Hi everybody, and we're going to continue with our lesson in linear algebra. We're still now in the topic of non-singular matrices or invertible matrices, and we're here on Theorem 1.5, which it states that the inverse of a matrix, if ever it exists, is going to be unique. So with this uniqueness, it follows that, remember from our remark, that we'd like to highlight that A times A inverse is equal to A inverse times A equals to I sub n, where n is the either the row or the number of rows or number of columns of your square matrix. So say for example, let's consider this example 2 where our matrix A is equal to the matrix 1, 2, 2, 4. We need to find the A inverse if ever it exists. So okay, let's try making use of this equation here above as a remark. We're gonna apply that. So solution, if A inverse exists, let me write that again. If A inverse exists, our A inverse will be written as A, B, C, D. You can make use of any variable if you want. A, B, C, D is just like, making things simple. Then we should, sorry, where did we go? Sorry about that. We should end up with making use of that theorem there. A times A inverse is equal to A inverse times A equals I sub, well, I'm gonna write it already, I sub 2. And thus then we have A times A inverse is going to be equal to, remember our A is 1, 2, 2, 4. Our A inverse is denoted by A, B, C, D. This is equal to I sub 2, and I sub 2 is equal to 1, 0, 0, 1. Further, let's simplify this. We have 1, 2, 2, 4 times A, B, C, D is equal to 1, 0, 0, 1. Okay, now what we're going to do is we're going to create some linear systems of this one. But before that, we would like to first multiply in a matrix format this one here and this one here. So with that, what we have is 1 times A plus 2 times C. So where did I get that? This one right here. Then for the 1, 2, we have 1 times B plus 2 times D. Where did I get that? It's over here. Okay, hope you see that. Next, entry 2, 1. 2 times A plus 4 times C. Where did I get that? It's right here. And for the entry 2, 2, 2 times B plus 4 times D. And again, here's where I get it from. Okay, so this is just simply equal to 1, 0, 0, 1. Now it's time to create our linear systems. Hence, thus we have the following linear systems. First, we're gonna write A plus 2C. I'm gonna omit the leading coefficients, the coefficients with the 1 on it, because that's gonna be automatic. So we have this where they get it from this expression here equated into this right side. So you can just imagine our lessons in augmented matrices. So we have a 2A plus 4C equals 0. Where did I get that from? Here and here. Okay, next, and we have B plus 2D equals 0. Where did I get that from? From this expression on the left side and this term on the right side. And lastly, we have 2b plus 4d equals 1. And this is where I get it from, for left-hand side expression and right-hand side term. Now, let's try to either use elimination or substitution here. And let's start with, of course, with our first linear system. I'm gonna call this equation 1 and equation 2 for simplicity. And I'm gonna make use of substitution. From equation 1, we have a. I'm gonna, of course, it's gonna be easy to substitute or using a. I'm just gonna isolate a here on this part. So 2c equals 1. This will give us a equals negative 2c plus 1. Okay. From here, using the value of a in equation 2, we have 2 times negative 2c plus 1 plus 4c equals 0. Let's simplify some bits here. So we have negative 4c plus 2 plus 4c equals 0. Simplify combine the like terms. Well, it's gonna be problematic from this case right here, because if we're gonna combine the like terms, we're gonna cancel out the c's. We're gonna be ending up with this equation here, which is of course a big question mark in the world of mathematics, because 2 is not equal to 0, obviously. And this just lets us know that there's no solution between the equations 2 plus 2c, a plus 2c equals 1 and 2a plus 4c equals 0, hence indicating that this right here is an inconsistent system. Inconsistent. Hence, there's no solution. So we can just say, maybe you can use this symbols. Maybe your book is using this. The solution set is equal to a null set, so there's no solution in this kind of one. We can also verify that on the second system that we have, and I'm gonna show that it's also inconsistent. So I'm gonna call this equation 3 and 4 respectively. So I'm gonna still make use of substitution. So I'm gonna use from equation 3. We have, of course, it's gonna be simple to substitute just b there. So thus we have b is equal to negative 2d plus 0. So I won't anymore use 0 there. Thus, or then, using the value of b in equation 4, we have 2 times b is negative 2d, right? Plus 4d equals 1. I think you can already see, it's like seeing a comet. It's coming through, and we can see that 2 times negative 2 is negative 4d, plus 4d equals 1, and the rest is history. We're gonna cancel this out, and it will give us 0 equals 1, which is again a big question mark. In the world of math, 0 is not equal to 1. This verifies that the system with b and d is also an inconsistent system, wherein your solution set is equal to the null set. So there's no solution that we can see right here. So this simply indicates, therefore, the linear systems have no solutions. Thus, A inverse does not exist. Therefore, if A inverse does not exist, A does not have an inverse. If that's the case, we therefore say, hence, we call A as a singular matrix. Also, the other term for a singular matrix is non-invertible. Non-invertible. Okay. Oh, sorry. It should have been this. Okay, so I guess that's it for this video. I hope you learned something from this, and thank you very much. We're gonna see you in the next one. Bye.